Hello and welcome back to Differential Equations. We have to start chapter 7 today, which is on Laplace Transforms. This is the used to be the favorite way for engineers to solve differential equations when they need to design something, because differential equations are using the tables and charts, right, to convert, watch this, or listen to this, to convert differential equation into a basic algebraic equation, then solve basic algebraic equation for the unknown, which is algebra 1, and then transform that back into functions and obtain solution. Holy nightmare, this is great, right? So you have some kind of a differential equation, whether it's electrical engineering, mechanical engineering, right, whatever, physics, it doesn't matter, right? You have first order, second order, 10th order, whatever order of a differential equation, and instead of going through all of the stuff we did, you convert that into a linear basic or a quadratic or something that it's very easy to solve. You solve it and then you go back, right? So Laplace transform is one of the most beloved methods, well, used to be most beloved methods in engineers today, not as smart as used to be, right? Because today you can solve all of these things using computers. You don't have to be smart to solve equations anymore. You just use a computer to solve it for you. But in the good old times when people were smart enough to solve these things, right, they used to love this method the most and use this method the most because it was the coolest, right? You do not have to worry about any of the methods that we learned so far. You can just use this and be done. Now it's dependent on conversion, it's dependent on integration and so on. So there are a few things that right, we still need to know. But for the most part, as I said, you can always use the table of values, right? And the tables are usually provided on exams for these things. Generally, when I teach this course, I provide the table in classroom, right? I provide a table of Laplace transforms, and I remove 5 of them, right? Those that are kind of very frequent and easy to remember. I remove those from the table and you get everything else. But now that you have a resource and you can cheat while doing the exam, then you can have all of them, I guess, in front of you and maybe learn nothing. I don't know. Anyway, let's take a look at what happens for Laplace transform. So this is going to be actually transformation from what we call t, time domain, into s, which is called a frequency domain. And once we do the transformation, the function will appear different because it will have a different variable and it will look differently, right? So when you completely change it like that, it's a transformation. So everything changed. The variable changed and the function changed. So what is the definition for Laplace transform? And obviously we're going to calculate a couple of these for the to show. So given function f of t for all t larger than 0, equal. Why just t larger than 0? Because we really don't care about less than 0, because it's time, right? And when you're designing something, well, at least you start now, and that's your time 0 because there was nothing before that time if you're designing something new, right? So you start with time equals 0, right? And so given the function f of t, where for all t larger than 0, the Laplace transform Laplace transform, which would be this capital F of S, is, and here it is. So F of S is the Laplace, that's the capital lowercase l of f of t, is going to be the integral from a to infinity. Well, you can do 0. We can start with any value, but 0. E to the negative st times f of t dt. Where, or we can say whenever, this improper integral converges. So this is your definition for Laplace transform, and you will be using this integral to transform your differential equation into the basic algebraic equation, and then you would solve that algebraic equation and get solve the algebraic equation, right, and get the solution, and then run. So, but that's 3 sections away, so let's not get carried away. So what do I need to transform this? Well, it should be obvious, right, because the word said so. It's improper integral, yay, right? So it's improper integral. But the other very important ingredient here is obviously integration by parts, right? Because you see that that's the form of integration by parts. And the third piece of the puzzle for the inverse part later on is going to be partial fraction decomposition. So clearly, if you don't know your Calc 2, you're just dead here. So you'll have to go relearn those sections, right? Because some people learn for a grade. So if you learned for a grade, now is a good time. Today is a good day, right? To go back and learn those sections for knowledge, because you'll need them in this section. Okay. So now that we know this, we can go and transform some of the functions, right? Because this is ultimately transferring function f of t into f of s. So in the end of the day, you take some f of t function, which could be t squared, sine t, e to the t, right? It's just some function that you are very well familiar with, right? It's a part of your differential equation. And you transform that into a function f of s, and now it's capital F to, right, denote that it came from f through the transformation above, and it is now, the variable is s. So another thing here, your integral is in terms of t, which means that all of the t's will be integrated out using the limits. Therefore, you will only have s as a variable that stays floating about. All right, let's go and do an example of transform f of t equals t. That's second cheapest, right, you can have, obviously. Would anyone write? Could anyone write what's the cheapest one to transform? Since we're dealing with calculus here, I'll let that linger, and then, because there's lag, just type it in what you think is the cheapest to transform. If just basic t, which used to be x, is the second cheapest. All right. Let's go and talk to. Let's do the transformation. So my f of s is going to be the Laplace transform of t a Ooh. Here it comes in with a constant. Two of you said a constant. Okay, so then that would make this one third cheapest. Oh my god, I forgot about constant. All right, you guys are correct. That's not what I was thinking of, but the constant is going to be cheaper to transform than the t. Yes. So t is the third cheapest. Wow, I completely forgot about constants. You guys are amazing. Love it. Amazing. Still didn't get the one that I was thinking of though. There we go, Jess. Yes, e to the t. Yes, e to the t is the one because both actually constant and e to the t would eliminate the need for integration by parts. You would just be doing one simple straight integral and we're there. Anyway, back to our problem. So we're supposed to transform t over here. And the way we transform t, we said that was the integral that was from 0 to infinity, e to the negative st, and then we'll multiply that by t dt. Right? So this is the problem. And in calculus, we usually had it as x times e to the x. So we are going to now do the limit because it's improper integral. So b goes to infinity, 0 to b. And over here I'll just have t e to the negative st dt. Now, s in this problem here is a constant. I understand that at the end of the things, s will be our variable, but as far as this integral is concerned, the only variable is t because the integral is dt. So s will behave as constant. And now all we need to do is to set up integration by parts and plow through this calculation, and we're done. Right? So integration by parts is, because this is polynomial times exponential, u is going to be t, dv is going to be e to the negative st dt, du is going to be dt, and v, when we integrate this, is e to the negative st divided by the constant, which is negative s. And then we do our trusty arrow, which is the formula. Again, if all of this is making 0 sense, back to Calc 2, back to integration by parts, look it up on my channel, find it somewhere else, doesn't matter, but this section is impossible without integration by parts, partial fraction decomposition, and improper integrals. There is nothing you can do in the whole chapter. So make sure you can do those. Alright, so now we have our te negative st divided by negative s minus the integral of e to the negative st over negative s dt. When we plug in integration by parts, right, using the formula, and now we have limit b goes to infinity. We have our te negative st divided by negative s, and over here we have plus 1 over s, you kick that outside, and you have to integrate this again, which will just spit another s outside. Alright, so we have to keep these parentheses in because this needs to apply to both terms. So we are keeping those parentheses all the way to the end. Limit b goes to infinity, te negative st divided by negative s, and now we have negative 1 over s squared. Holy nightmare. E negative st, there we go. Negative s squared. Now, we don't have a plus c, this is a definite integral, right? So we are using 0 and b to compute these things. I should have written 0 and b along the way, it's just that lazy, right? So it's a definite integral, and we will, oops, my parenthesis points off right there. And now I am supposed to plug these values in. So, limit b goes to infinity. Plug in b everywhere. So that's b e to the negative bs, negative s. And then now we'll plug in 0. We'll get negative 1 over s squared. That's from 0. And then we'll have plus. No, wait, this is a b. This is e to the negative bs. It should be sb, but whatever. Now we plug in 0. 0 will kill this term, and then make this one into minus, and minus will give us a plus 1 over s squared. There we go. I was concerned about that. And now, when we send everything to infinity, right, all of these will drop to 0. So this term goes to 0. This term goes to 0. Now, this first term, right, the both terms go to 0, and the whole thing becomes 1 over s squared. Now, before you scream, but hold on, this one is going to infinity and this one is going to 0, how do we know which one wins? This is linear, that's exponential. Exponential always win. Don't believe me? Well, L'Hopital rule is always there to make your life, right? Oh, this is the constant. You just scratch that for the limit, right? No one cares. You look at these two functions here and you say, I have exponential versus polynomial. There is no contest there. I mean, exponential is obviously stronger, so just, you know. And what we have found is that our f of t equals t transforms into f of s equals 1 over s squared. This is in your table of Laplace transforms. I'm not sure whether that's on the front or on the back. Back of the book appears to have table of integrals. Maybe front? Yes! When you open up the cover of your textbook, the first page has the values. T is all the way on is a fourth from the bottom. Fourth from the bottom on the, yes, thank you, yes. So when you open the front of the book, fourth one from the bottom gives you the 1 over s squared. Perfect. Okay. The question is, how about the rest of this chart, right? We can obtain all of them. Sure. And, one of these will be on your exam to take. By the way, talking about the exams, exam 2, chapters 4 and 5 needs to happen as soon as possible. And then some people were saying, I had conversation with some people, to have exam 3 cover the rest and not have the final, or have the final that it's cumulative from the beginning of the course. There will be that homework open for you anyway as a survey, so I guess I'll have to post in announcements and then see where you guys stand. You have to have exam with Laplace and series on it, but so that's going to be either exam 3 or the final. We'll figure it out. All right, so let's go and transform. Say f of t equals e to the 4t. Let's say e to the 4t popped up in your calculation somewhere, and you need to transform that using Laplace starting next section or following section, right? You need to convert this. So what happens here? How do you convert this mess? Well, we do the same thing, right? F of s is going to be the Laplace of e to the 4t, which is what we are plugging into our 0 to infinity integral. e to the negative st times e to the 4t dt. Didn't we already have it? No, that was the midterm. Ah, yes, you're right. So we're, yeah. See, I'm not supposed to talk about these things while I'm teaching. I don't know why I get sidetracked. Now we're losing momentum here. Yes, exams 1 and 2 were combined into midterm. You're right. Exam 3 is going to be on chapters 4 and 5. And then we're either going to have a final, which is cumulative, or exam 4 on Laplace and power series only. Depends which way you want to go. Yes, you're right. So, yeah. All right. Anyway, going back to this simple algebra here, we do our limit. B goes to infinity. We always have to have that. 0 to b. And look what we have. We have e to the 4 minus s times t dt, because exponents add, and when you add these two exponents, right, you in factor t, you get minus s plus 4. Well, that's 4 minus s. So now that's a constant. That is a constant. So it's very easy to integrate this one. There is nothing special going on, right? The limit of e to the 4 minus s divided by 4 minus s, times t, from 0 to b. And now you plug in the values for t. So we have our limit, b goes to infinity. We have our e to the 4 minus s times b divided by 4 minus s, minus, when you plug in 0, 1 over 4 minus s. Now, what happens here? Well, I'm supposed to plug in b goes to infinity. And this is going to, I'm going to do this algebra. You will hopefully be skipping this algebra later, but right now you need to know. So this is e to the 4 b times e to the negative s b divided by 4 minus s minus 1 over 4 minus s. We don't need the parentheses here because this one has no b in it, so it will not be affected at all by the term. Now this term goes to 0. And this term goes to infinity. So what should we do? Right? So you can do L'Hopital rule from Calc 1. And if you go through L'Hopital's rule, you will get that the limit is 0. So the answer will turn out to be 1 over s minus 4, because this negative will distribute and change the order. Now let me see if you go here and you take a look at the transformation. I went to the book, the front page, and took from the table that e to the at transforms into 1 over s minus a. Now, what was my problem? My problem was e to the 4t. That transforms, because a is 4, obviously, into 1 over s minus 4. This is why engineers like Laplace. You have a table of integrals, table of transforms, and you don't have to go through the grind of calculation to get your 1 over s minus 4. You can look at the table, figure out what your a is, and just replace it, and you have your f of s, right? So f of s is equal to 1 over s minus 4. So that's why people absolutely love Laplace transforms. Let's take a look at one more calculation here. So there are, some of these are obviously messier than others. We have sines and cosines, and then hyperbolics, and then e times sines, and these are all obviously very important for, so anything that has the sine, cosine, and sine, cosine, hyperbolic, and also mixed with exponentials, that's very important for mechanical and electrical engineers. And the reason is you have oscillating systems all the time, right? For electrical, you have your AC circuits, and for mechanical engineers, you have your pendulums and spring mass systems. And you know that a lot of stuff is powered by springs and any kind of and rubber bands and things like that. So I mean, technically materials, right, that you use. So these are very, very, very important. And let's take a look at the transformation of one of these. Now, instead of proving the formula, which is something like here that I did just in general terms, I'm going to work out on a particular homework example where I'm going to have, let's say, sine of 10t or whatever, right? So let's say that f of t is sine 10t. What is f of s? Now, obviously, right, if you have sine of 10t, the answer is 10 over sine over s squared plus 100, right? That's clearly the answer. Why? Because you look at the table and you are done in 2 seconds, right? But we just want to do one of the calculations because this is a math course, right? And you are supposed to know in the math course how to compute basic integration by parts. So, you know, calculation like this is your homework example, and obviously something like this that shows up on the test. Again, test will be either test 4 or final exam. So that's what we have. All right, so what do I have? I have f of s will be Laplace transform of sine 10t. Oops, gotta be curly bracket at the end. There we go. And that's going to be our integral 0 to infinity e to the negative st times sine 10t dt. So now those of you that are cursing because you already know that this is the double integration by parts problem. Yes, right, this is the double integration by parts problem. There is a way to solve this using complex numbers in literally 2 lines. But, you know, such is life, right? We can also do a page of calculations instead. Even though it will be very beneficial for you guys to learn how to do that with the complex, because it's fun and will keep unnecessary people away. Limit b goes to infinity, 0 to b, and here we have our negative e to the st sine 10t dt. All right, so just to make sure, I will be testing you a lot along way this calculation, so pay attention to catch every time when I test you. All right. We start with pinning down u as e to the negative st, which would leave as a dv our sine 10t dt. Our du will be negative se to the negative st, and our v will be the integral of sine is a negative cosine 10t divided by 10. And then we use our trusty arrow here for the formula. Limit b goes to infinity, open parenthesis, and let's write this mess. That's going to be negative 1 over 10 times e to the negative st cosine 10t. And now my integral will have a minus, and both of these guys have a minus, so that's altogether 3 minus signs, so it's a minus. We can kick s over 10 in front of the integral, which is 0 to b, because those are constants, and you just have e to the negative st time cosine 10t dt inside. And at this point in life, right, you are supposed to do this calculation again. So negative 1 over 10 e to the negative st cosine 10t minus s over 10, and now another integration by parts goes in here. Maybe I should just start it here. Minus s over 10 open parentheses, so we can fit another integration by parts, and I am going to go orange here and say u equals e to the negative st, dv equals cosine 10t dt, du equals negative se to the negative st, and the v equals sine 10t over 10. And I will put the arrow again for our formula. So what goes in here? It goes 1 over 10 e to the negative st times sine 10t. Now minus and minus will give us a plus in here. And then that plus, it's going to be s over 10 integral 0 to b e to the negative st sine 10t dt. There it is. All right, perfect. And then we close the main parenthesis. Just a little bit of algebra is not a big deal. Did I mention to put your notebooks landscape? No, I didn't. That's because I'm a terrible instructor. Limit b goes to infinity. We have a negative 1 over 10 e to the negative st cosine 10t minus s over 100 when you multiply. Right now we're distributing this one on two terms. So you are getting negative s over 100 e to the negative st sine 10t. And you are getting minus s squared over 100 integral 0b e to the negative st sine 10t dt. Got it. Whew. So now, this one over here is the same term as the one on the other side. So what we have is the original problem, which is integral 0 to b of e to the negative st sine 10t dt plus s squared over 100, because this, when it goes to the other side, becomes positive, right? Integral 0b e to the negative st sine 10t dt is going to be equal to this mess, limit b goes to infinity, negative 1 over 10 e to the negative st cosine 10t minus s over 100 e to the negative st sine 10t. So nothing else exists from before. That's it. This is what we're looking at. And dare I say clearly, right, you are supposed to add the two integrals on top, right? So when you factor out your integral, you get 1 plus s squared over 100 times the integral of your transform, which is what you're looking for, equal to the mess you see below. Now, the mess you see below is from 0 to b, and you can solve it because that's all integrated and done, right? So you can just go and say limit b goes to infinity, and you have your negative 1 over 10 e to the negative bs cosine 10b minus s over 100 e to the negative bs sine 10t. And now we plug in the ones with the 0, right? So that's going to be plus 1 over 10. 0 is making this e into 1, and a cosine of 10 makes it into a 1. And then a minus sine of 0 will be 0, so that would be all one big fat 0 right there. So now add these fractions. You are going to get, so these are all like their own separate, right? Left equals right, left equals right. So here's the left equals right between the orange lines. Here's another left equals right. And this whole mess over here with 2 integration by parts was also left equals right. So these are all separate steps. So finally now, common denominator is 100. So I'm getting s squared plus 100 over 100, integral 0 to b, e to the negative st sine 10t dt is equal to, okay, now we do the limit. Let's do the limit. When I plug in my infinity, this guy goes to 0, this guy goes to 0, and also, and by the way, when you plug into infinity, these guys have no limit, but they are bounded between a negative 1 to 1, right? So cosines and sines in the limit, they, unless its limit goes to 0, right? If the limit is going to infinity, they oscillate between negative 1 and 1. They're bounded, right? So 0 times whatever value you pick between negative 1 and 1 is going to drop all of those to 0. So this is all equal to 1 over 10. And now I need to get my integral alone. So here is another step, left equal right. So multiply both sides by 100 over. So integral 0 to b e to the negative st sine 10t dt is equal to 1 over 10 times 100 over s squared plus 100, which is 10 over s squared plus 100. So my f of t, which was sine 10t, transformed into f of s 10 over s squared plus 100. Now, our problem is done and solved. And it took some doing, obviously, right? Some effort, but we got it. If you look at the back of the front of the book, not the back of the book, it says like this. if your f of t is sine kt, it will transform into k over s squared plus k squared. So your problem of sine 10t, you know your k is 10 because you use your eyes, you look at it, right? And you get your 10 divided by s squared plus 100. Apparently page 442 has it as well. Oh, nice. The best of. Yes, I love it. If you go to page 442 in a book, you have the best of. It's missing though e times sine and e times cosine, and those are very important because when you have your damped oscillations where your oscillation actually dies out, which is what we are experiencing in what you would call the real world, because this is fake, you have to have for your oscillations those. I'm just gonna draw that same graph again. If you have a pendulum or a spring or whatever, right, they're all pretty much the same thing. So pendulum that it's swinging back and forth, right, between these locations, goes back and forth, back and forth. The motion x of t distance, which you can later differentiate into velocity, differentiate into acceleration, differentiate into jerk, right? So you can do stuff. You just need to know position and let the calculus take over, right, for the rest of the stuff. Your position x of t will be given with some form of negative a t, and then depending on where you started, right, you will have this form. So transforming this is very frequent when you are dealing with electrical circuits which have inductors, obviously AC, and mechanical systems with dashpots and pendulums and things, dealing with, because the gravity and air resistance will slow down and eventually stop your pendulum. So if you want a realistic picture, right, you have to use the dashpot, right? You have to use calculation, and the formula will come out this way. Now the graph for this x of t, just to push this little bit more. So this is your time axis, this is your x-axis, which is your distance, and you have this e to the negative at graph, which goes, right, exponentially decays, and it creates this sleeve. And now that I think I'm going to change this to sine so it's better on the picture. So if I start with my sine, goes up, goes down, up, down, up and down, up and down. And then eventually, as the time passes enough, you see that the displacement between the equilibrium and where the point is zero, right? Because it stopped. And it's this term e to the negative at that makes it stop. Now, in our problems from before, that term only appears when you have a dashpot, when you have gravity, when you have air resistance, and all of these things that you actually have. Now, if you go far away between two galaxies where the gravitational pull is zero and cancels and so on, right, your pendulum will swing forever. If nothing else bothers it to create this e to the negative at term, right, the pendulum will never stop. So it's important to know how to transform these, and they're given on the right-hand side. So you pick your a. Here a is positive, so you just pick your a to be a positive, negative number actually, and you do the transformation. And you can practice those, those of you that are a little bit interested in these things, right? You can develop and practice your own formulas. All right, let's see. So page 442 has the best of for these. Now, what's important for us going forward is the property of linearity of Laplace transforms. And the reason why that is so is you guys are going to have multiple Laplace transforms, or Laplace transforms that are complicated. Maybe you can break it down and things like that. So linearity, this is a very important theorem. Linearity of the Laplace Laplace transforms. That's the full name. Usually we just say Laplace, or when you are solving these problems, you're trying to explain something to fellow teammate or whatever, and you just say Laplace it, right? So you apply Laplace transform. You just say Laplace it. And by the way, you are not successful in life until your name becomes a verb. Okay, so there you go. That's something to strive for in life. So when your name becomes a verb, then you made it. So now we get to Laplace things all the time, right? We'll Laplace things, and we create technology by Laplacing things. It's amazing. Anyway, what is the linearity formula? It simply says that the Laplace of a f of t plus b g of t, if I have two functions that are added, is going to be sum of separate Laplace transforms. So a Laplace of f of t plus b Laplace of g of t. Guys, this is equivalent to breaking two functions within an integral into two separate integrals, doing two separate derivatives on functions that are added or subtracted. This obviously works on subtraction as well, but subtraction is not real, so we don't use it here, right? You can have a subtraction as well. I say subtraction is not real because a minus b can be written as a plus negative 1 times b. So subtraction is not real. Does not exist. The only two things that exist are addition and multiplication. That's it. The rest, we don't need anything else. All right. Well, you will know that once you take linear algebra. Right now is just some lunatic talking, but when you take linear algebra, it will put those things in perspective, and you will see that, division and subtraction are unnecessary. They're convenient, but unnecessary. Cool. So, what should I do here? Maybe jump into a homework exercise and see if they are asking you to solve any one of these. Maybe, yes. Nice. Problem number 12 would be an excellent problem to consider. They want you to transform f of t 3t to the 5 halves minus 4t cubed. Should have gone for 14 because it has e in it. Or 6. Yeah, we'll do one more. Whatever. Such is life. Okay. So, need to convert that into f of s. Right? So, what should I do here? Well, clearly, I am not going to go through calculations with integrals and stuff. I'm just going to use the table because I want to work on the red formula, not do the definition again. And so this one will be transformed using t to the n, and this one will also be converted using t to the n. How boring. And t to the n is n factorial divided by s to the n plus 1. Now, I know for a fact that all of you learned factorials at least twice in your life prior to this lecture. So you must know that n factorial is 1 times 2 times 3 times times n at the end. Right? So yeah. So now we have an issue here because t to the n is not going to work because n factorial works on integers. 1 times 2 times 3. There is no 5 halves. 5 halves is 2.5. It doesn't work in a factorial. So we can't use this one here, t to the n. We have to use t to the a. And t to the a has a very interesting solution, something that we need to talk about, which is a gamma function, hello Riemann, over SA plus 1. The hell is the gamma function now? Well, we have to deal with the gamma function, right? So gamma function is a function that allows you to deal with these functions that have exponents. So gamma function of x is defined as integral 0 to infinity of e to the negative t times t to the x minus 1 dt. And that will give you, when you integrate this out, it will give you the function of in terms of x. Now we are entering the realm of functions that are defined through integrals, and there are a couple of them, like SI function, LI function, ER function. It's like a whole bunch of them that are defined as the integral that you generally can't compute, right? So gamma functions are in their own right, special creatures. So we are getting a function as gamma function of, and then you would have to compute the gamma function for that. So let's deal with the gamma function first, because that's a new creature you haven't met before, and then the one on the other side is a joke, the orange one. So what do I have? Well, when I look at the problem, I see that my a is 5 halves. I'm going to actually box this as a formula. So, right, this is called the gamma function. And the letter you see there is a Cyrillic letter, capital G. So in Cyrillic, which is my native, right, you have A, B, V, G, D, J, and so on. There it is, G, gamma. It's very close to what the alpha, beta, and then they have gamma, lowercase gamma, Greek. Like, so a lot of the Russian language, obviously, and Serbian, and they have a lot that use the Cyrillic alphabet, and then Greek is close, right, as well. So capital G for but it's this G like that. That's all it is. It's just but it's capital. All right, so let's go and deal with the gamma function first. So I am supposed to, since the a is equal to 5 halves. A is equal to 5 halves. I am supposed to now compute gamma function of 5/2 plus 1 divided by s 5/2 plus 1 in the exponent. Well, this is compute gamma function of 7/2 divided by s 7/2. So we are going to compute gamma function on the side, right? We're going to compute, so let's compute gamma function on the side, and then I have to compute gamma of x is equal to 0 to infinity e to the negative t, and then t to the 7/2 dt. I gotta go get some water. I'll be right back. Okay, so gamma functions. Now we're supposed to compute the gamma function, right? But we can't, right? Because you can do your improper it's improper. Integration by parts here, because this t to the 7/2 will never go away. And e to the negative t will never go away either, right? So the answer will contain gamma function definition in it. So this part means this divided by s to the 7/2. That's what it means. Now let me just do one thing on the. I'm going to check. Going to Wolfram Alpha right now. Integrate. All right. One second. And okay, great. So it does show error function in it. Perfect. So the value is 11.6317, but The calculation for this is, it's graduate work. There are ways to deal with this, but we are going to leave the answer in terms of the gamma function. So that's the left-hand side, and the right-hand side is cheap. So right-hand side in orange is going to be n equals 3. So it's 3 factorial divided by s3 plus 1, which is 6 over s to the 4. So now what do I have? I have capital Fs, which is our Laplace transform, is going to be gamma of 7/2 divided by s to the 7/2, and that's times 3 minus 4 times 6 over s to the 4. So the answer that we are providing is 3 gamma function of 7/2 divided by s 7/2 minus 24 over s to the 4th. So that will be the answer. Now, the gamma function in this case of 7/2 is approximately equal to 11.6317. Software. Again, there are ways, graduate school, right? There are ways to compute these things, but we're not going to spend time on computing that right now. You're just leaving it as the gamma function, which you can actually compute and just get a number. Now, you see that the domain now is, we call this frequency domain, so it's a completely different domain. Now I wanted to do another problem with trig. So we have problem 16, where f of t is equal to sine 2t plus cosine 2t. All right, so let's take a look at the sine and cosine here. So this one will convert using the sine. Our k is 2, so it's 2 over s squared plus 4. And this one is s for a cosine over s squared plus 4 when you convert them. Well, we're done. Just put a plus in between, and that's your f of s, done. You just look at the chart. So the whole thing converts to s plus 2 over s squared plus 4. This one does not factor anything. All right, so I believe this problem was on now we're talking 12 years ago, an NGIT differential equation to transform, and it was absolute massacre. I mean, you always have students that are going to get it, but so something very similar to this, and such a simple problem when you know trig. First of all, your linearity works only for addition and subtraction, and you should know that for all of calculus, products and quotients have their own formula. Linearity only applies to addition and subtraction. So you cannot transform these two and multiply it because it will be terribly wrong, right? So what do you actually how do you actually solve this problem? You solve it using a basic pre-calc 2 trig formula. You compress this into 1/2 sine 6t using a basic double angle formula. Because a sine 2u is equal to 2 sine u cosine u. So your basic formula there, and then your sine transforms as a k, which is now 6. So it's 6 over s squared plus 36. And you have a half in front. So your f of s is just 3s squared plus 36. That's it. So by use of basic trig identity, right, you are transforming this into a single trig function, and you're done. So we spent an hour talking about forward transformation, which means you have a function in the time domain, f of t, and you are converting that back into a frequency domain S, which is capital F of S. That's a frequency domain. Great. So we're done there, right? The next objective for us is to go backwards. Let's not lose, I'll just write this, inverse Laplace transform. Let's not lose what this is all about. You have a differential equation given as f of t's. You have your derivative double prime in terms of t, derivative prime in terms of t, right, f of t. So everything is in terms of t's. So that is your equation, differential equation, given in what we call the time domain. Your job is to transform that using Laplace, and you will see that when you transform it using Laplace, you will get the function for in S. And that will be a basic algebraic equation that you can solve. We'll see that, right? Why are we learning inverse Laplace? Because once you solve that equation in a basic algebraic equation in a frequency domain, you have to go back into time domain to present your answer, right? So pretty much the same like U sub. When you transform it using U sub, well, not pretty much, it is the same. It's the same idea. You transform your X domain into a U domain, you solve the integral, and you go back to X domain to present your answer, right, plus C. So you will do the same here. Once we transform it into the S domain, I need a way to go back into the T domain to present my solution. Now for this one, we will have to use inverse Laplace transform. So we are looking for the definition that says that f of t is equal to inverse Laplace of f of s. And again, you are using the chart and all of those things to come up with the transform. Now you're going to say, wait, hold on, but this is it, there's no formula for us to compute and stuff. You have the charts. You have the charts, and you have to look at the chart and figure out, because once you solve your equation, you are going to get some mess in terms of numbers. You will get, let's say you get 3 3 over s to the 5. Right, that's your f of s. And you are supposed to go into f of t. Right, so how do you do that? Okay, so what do you first look at the table of values, right? And you go and you say, there is that t to the n. Okay, so we have where t to the n transforms into n factorial over s to the n plus 1. So when I compare this to 3 over s to the 5, I can see that n is equal to 4. Okay. So what do I need for this to happen? If I just have t to the 4, then that will transform into 4 factorial over s to the 5, and 4 factorial is 24 over s to the 5. But I don't have 24, I have 3. So I need to multiply this by 1 over 8, and if I put 1 over 8 in front, then it's going to work to be 3 over s to the 5. Oh, okay, there it is. Yeah, you have to do this, literally. I'm going to do it from scratch. And then we'll do other examples. So what have I done? This is the problem that I need to convert. I look at the chart in a transformed Laplace, right, f of s column, and see what is close to it. And the one that is close to it is this t to the n business. Okay, I have t to the n business. So, see, this needs to equal 3s to the 5. This is what I need. So now figure out everything. Right? Figure out everything. This is what I need. So what's going to happen here? Well, when I compare the bottoms, right, these denominators, I know that n is 4. But as soon as I put n is 4, I get this spinned, right, in the formula, I get 4 factorial over s to the 5. Well, that's 24 over s to the 5. But I can't have 24 because I need 3. So I also need a coefficient of 1 over 8 in front, because that's going to reduce it down to 3 to the s to the 5. So f of s given as 3 over s to the 5 will convert into f of t that will be 1 over 8 t to the 4. There we go. So that's where it came from. And you have to do this every time. You have to be figuring out this part. Let's take a look at another one. Say you have 6 over e minus 4. Six over s minus 4. This is f of s. All right. So, what is f of t for this? Again, you go to the chart and you find that this form is closest to 1 over s plus a, which is e to the at. Right? So to get my s, right, to get my 6, I multiply both of these sides by 6. So this is going to be now, and a is negative 4. When we compare this and this, a is negative 4. So, and I need times 6 on top. So f of t must be 6e to the negative 4t. It's going to take some practice to get used to this mess, but you can do it. Let's take a look. Another one. Say it's s, 4s, over s squared plus 81. Okay, well, you would say that's a 4 s over s squared plus 81. 81 is 9 squared. Now you see that the whole piece over here is a cosine, so 4 converts into 4 cosine 3t. Oh, no 3t, 9t. Sorry, it's 9 squared. 90. 90. So f of t is 4 cosine 9t. Easy? I guess. Because we look at the chart and we find the value, right? Then we find the closest one, and then we work on it to fix the constants and coefficients and all that kind of stuff, and it just works out. Let's open the gates of hell. That's tough on top? Okay. F of s equals 3s cubed plus 144s minus 72 divided by s minus 2 s squared plus 36. Yes. It will pop up to be a solution like that, and then you need to convert it back into the t domain. And whatever we do now, it's still going to be way easier than if you actually tried any other method, differential equations. Remember, Laplace is always your friend. Well, it's all fun and games till someone loses an eye, right? So when you're looking at this one, you need to inverse Laplace it. You are looking at these on the bottom and you're saying, oh, that's exponential, that's sine or cosine, but only if they are separate. They're all on a pile here. So what now? And this is where your good old friend from Calc 2 kicks in. That friend is known as... Let's go chat, 10,000 people, everyone is excited. And out of 10,000 people, 9,980 knows what this is. Partial fraction decomposition. Very good, my friends. Yes. So we go with our A over S plus B over S minus 2 plus CS plus D over S squared plus 36, because that cannot be factored any further. You apply your partial fraction decomposition. So partial fraction decomposition from Calc 2 goes here, and we get A is equal to 1, B is equal to 3, C is equal to 1, D is equal to 0. And now we have our f of s to be 1 over s plus 3 over s minus 2 minus s over s squared plus 36. So that's Calc 2. Partial fraction is done also in Pre-Calc 1 at the end in Chapter 7, I believe 7.3, 7.4, whatever. That's where you were supposed to do it for the first time. And then obviously you have the whole section on it in Calc 2. We use the partial fraction decomposition here and there sporadically, right? But right now it's kicking back with vengeance, right? The inverse Laplace. And good. Now what do I get? I get A is equal to 0. A is equal to negative 2. K is equal to 6. Perfect. So what is my 1 over s? S just going to be 1 because this is e to the 0, t. So when I write my f of t, I get e to the 0t plus 3e to the negative 2t minus the cosine 6t, and this e to the 0t is just 1. So when you are doing y minus s, oh, because c is negative 1. Oops. Thank you for. No, I was just testing. Yeah, I was just testing you all, and very good, very good. That's a point for you. All right. So when you do partial fraction decomposition from Calc 2, it says here goes. Calc 2 goes here. There we go. Very good. Perfect. Perfect, perfect, perfect. Let's see a homework problem. We'll do this one in full because we can. Problem 30. F of s is given as 9 plus s divided by 4 minus s squared. Okay, when you have s squared plus a number, then it's sine or cosine, right? But in this case, you have this one, which factors into. Well, when I switch these, we'll have a minus in front of the whole thing, and I'll have s squared minus 4. So this is s plus 9. There's a minus there in front, and then you have s minus 2s plus 2. So my partial fraction setup is a over s minus 2 plus b over s plus 2 to be negative s minus 9 over s minus 2s plus 2. When I cross multiply, I'll do the partial fraction, whatever. As plus 2a plus bs minus 2b, or not 2b, equals to negative s minus 9. So a plus b equals to negative 1, and 2a minus 2b, or not 2b, is equal to negative 9. I multiply the top equation by 2. I add equations that kills b. 4a is equal to, that's a negative 2, negative 11, I hope. And a is negative 11 over 4. So b is going to be negative 1 plus 11 over 4, which will give us 7 over 4. And I'm keeping one eye on the chat and one eye on this. I'm going to be cross-eyed by the end of this class. So I have a negative 11 over 4 divided by s minus 2 plus 7 over 4s plus 2. So that's our f of s broken. And now I have that my a is negative 2 and a is positive 2. So f of t converted is negative 11 over 4 e to the negative 2t plus 7 over 4 e to the 2t. And just walk away. Walk away slowly, back up and be gone. Now, I know that all of you by now are, PhD in partial fraction decomposition, but there is this one thing. Just keep this in mind, right? Don't get confused. If you get s squared plus a number, that's already done. Those are the easy problems, all right? If you have problem, let's say 28, if you already have what it says, 3s plus 1 divided by s squared plus 4. This is already set up for sines and cosines. You have your 3 times s over s squared plus 4 plus 1 over s squared plus 4. Your k is 2 in each one of these. The one with the s on top is a cosine, so you just write your f of t, 3 cosine 2t plus 1 times sine 2t. There is nothing to do here. There's no partial fraction decomposition because you cannot factor s squared plus 4 and you don't have another factor to work with. Partial fraction decomposition works only when you have 2 factors or more. This is only one factor. So you can't do anything here other than, can't do anything. You can just solve the problem right away because there is nothing else to do. Cool. All right, so now the question is, talk a little bit about graphs and then be done. That's all we have. So we already have seen the graph for that trig function where there was a dampening and all of that stuff happened, right? So what is the correlation with these graphs between, right, the time domain and the frequency domain and how they work? Because sometimes you will see that the people who really understand this, they don't even write equations. They draw 3 or 4 graphs and and they were done, right? Especially, when you understand what is going on. So when you working with signals and things like that, right? You have your functions, right? You have your functions in time domain and you have your functions in frequency domain. And so what is in a time domain? In a time domain, you are going to have your function f of t equals t, and the graph for that is your good old 45-degree t. But actually, hold on. We're going to start at 0 because for t larger than 0, right? And the frequency domain is the frequency domain will be your conversion of this. So over here you will have f of s, which is 1 over s squared. That was our first problem. And the graph for 1 over s squared looks like this, but we don't need this one, right? We're keeping s larger than 0. So we only have this one, and this is your s domain. So when you convert time domain and frequency domain, what do you know from before, right? You know that the frequency and period are inverses of each other, right? Do you remember the formula where your period p was 2 pi over b, and the b was in your, when you write your cosine, it was cosine b bt, right? So that number there, right, is related to the period, but technically it's that's a frequency right there. So they always have this inverse proportion, and you can kind of see that on this graph, right, where one shoots up and the other one shoots over. What else would be easy to maybe I should just draw this, right, to split the two domains. If your input function f of t is just a signal 1, time 1, that's all it is. So you hold that input, your frequency domain, 1 over s. Oh, by the way, time larger than 0, s larger than 0. There we go. S. This one is known as the unit step function. Which is the most important by far than anything else. Because that's where you give the input, right? And then you can just scale it with the amplitude to how much of that input you want. You want 12 volts? Great. 12. Click. 12 volts DC on. 9 volts DC on. And you can delay that input by shifting it So it's 0 before till some value a. So, and then you jump and you create the signal. So let's go blue, I guess. Nothing, nothing, nothing. Beep. Right? At t equals a, you turn the signal on. Yeah, it's just flipping the switch. Turn the circuit on. Right? So what it does, it creates the I did not write that this is u of t, right? That's the name for this function, and this is u of t minus a. I hope you remember from pre-calc 1 all the way back that when you are shifting functions to the right, you shift function to the right, you subtract the value by how far you moved it, right? So when you do that, you are gaining on the other side, right? On your f, I just flipped the book to take a look at this conversion, e to the negative as over s, which is a shift of the. Now the graph for this, I'm going to really quickly steal this from Desmos, because you are dividing decaying e to the negative x graph by x. So it's not just decaying graph. So e raised to the negative x, all of that divided by x. And it pretty much looks the same. It has this piece on the negative side, which we don't care about. So it's still a decay graph. It just decays much faster than there we go. And that's our S domain. So when you compare now the two, right, problems that are stacked, you see the one when you turn on the signal, the frequency decays slower than when you turn the signal later, it drops down quicker. Nice stuff like that. I think we have beaten this one to death. There is nothing else there. We're going to take a look at, so on Wednesday, we are going to transform our initial value problem, right, our differential equation problem, to Laplace, solve the basic equation, go back. What is this? 7, 3. Oh, there's the partial fractions again. Oh, actually, wait. Oh, that's translation. Okay. So partial fractions again, 7, 4. So we have to do at least 7, 4. And then we'll have to figure out, to get to power series. We're only left with 4. So now let's talk about the exam. What I was thinking is to open exam either on Saturday or Sunday, and then keep it open Monday, and maybe so you have a weekend to study and get better with chapters 4 and 5. I was thinking on opening the first quiz today, actually, and then go through, and then you guys can take the exam you know, Sunday, Monday, maybe even Tuesday. So how about Sunday through Tuesday, huh? Sunday to Tuesday sounds good? Chapters 4 and 5. Exam 3, so there is no confusion. Midterm was 1 and 2. Sunday noon to Tuesday noon. Because it is, Michael. It is exactly that. Yes. The answer to all of that is yes, yes, yes. So chapters 4 and 5, they're a mess. The exam on Canvas went really good for my pre-calc and calc. So I will definitely be using Canvas. I just have to do the exam review on Friday. Yes. Friday will be the review. Now I'm going to plug all of this then now into Canvas so we all have the same. Just find your differential equation class. Where's the spring 2020? There we go. So I'm going to plug all of this now in the announcement. And then you guys can log on the Canvas and keep posting underneath. So we said exam 3 on Sunday through Tuesday. And I'll give the details underneath. All right then, I will plug this in. I have a next class coming up, so I have to go. I'm going to plug this announcement real quick and then go to my next class. Bye all.